Okay, so today we're gonna go ahead and start the review for the AP exam. This is gonna be a review till you drop format. I'll go as long as my students here are willing to go. I just kind of went over the layout of the exam. 18 to 22% of the questions are going to be unit 3. Sorry, I forgot to put unit 3 here, which is intermolecular interactions, and 18 to 22% are going to be questions regarding acids and bases. Every other unit or every other topic is going to comprise about 7 to 9% of the questions. What we're going to do today is we're going to go over the free response questions released from last year's exam. Okay, and we're going to go through these one at a time. I'm going through the free response questions because these kind of cover all of the topics, and it gives us an opportunity to kind of practice everything in a holistic way. And then if we still have energy to go, then we'll go ahead and we'll do the practice exam questions, the multiple choice, and then unit by unit if we're still around. Okay, you guys are making faces because I just explained all this. I forgot to hit record. Okay, so this is the first question. We're going to work through it, like I said, one question at a time, and we're going to see if we can explain some of the topics that maybe we didn't get to cover in class in great detail. But most of the stuff that we're going to see, guys, you've already seen. We're just going to apply it in a different way. Okay, so the questions are going to be free response. All right, each question should take you about 23 minutes to answer. So it's going to be, obviously, we're going to take a little bit longer than that because I'm going to give you guys some background. You're going to have about an hour and 23 minutes, I believe is what it is, to answer all of these questions. And then it gives you at the top, it gives you how they're going to score it. Now, the AP exam is going to be set up where 50% of your score is going to come from these questions. And then the other 50% is going to come from the multiple choice section. All right, so let's go ahead and get started. It says, write your response in the space provided, following each question. Okay, examples and equations may be included in your responses where appropriate. Please make sure you read directions because in certain questions, they will ask you, they will specify that they don't want calculation. Okay, they want you guys to understand the concept. All right. You must show your work to receive credit for your answer. Pay attention to significant figures. Significant figures are going to be very, very important. All right, real quick. Melita, you're on my screen. Can you read this or is this too small? Because I'm looking at it on my big screen and I want to make sure that on your computer it's legible.
Yeah, I can read it.
Okay, cool. All right. So the compound urea is H2NCONH2 is widely used in chemical fertilizers. The complete Lewis electron strat diaphragm for the urea molecule is shown above. Identify the hybridization of the valence orbitals in the carbon atom in the urea molecule. Okay, so what is hybridization? Let's take a look at the molecule or the atom carbon. So we're going to talk about hybridization. I think I spelled this right. Oh, it's right here. How am I going to misspell it if it's here? Okay. Let me turn my volume down so I don't have an echo. Okay, so what is hybridization? Let's take a look at carbon. So if we take a look at carbon and we do the electron configuration. You guys all remember how to do electron configuration, right? So go ahead and write the electron configuration for carbon. I'll give you guys about 30 seconds and then I'll go ahead and start writing it. Just realized I don't have a periodic table at my disposal. Go ahead and open one up real quick. All right. All right. So we fill out the electrical configuration, and if we were to write it out in shorthand notation, right, orbital notation, it would be 1s2, 2s2, 2p2. Okay, this is all review. Okay, so let's take a look at carbon. All right, and that's exactly what we're looking at. So when you take a look at a compound like carbon, you see that the electrical configuration occupies two of the subshells in the p orbital, right? So really, we have space here to bond just these, well, let me change color here. Just in these three places, right? 1, 2, 3, right? We have a location to accept electrons in 3 subshells. But the problem with carbon is carbon actually has, looks like this. 1, 2, 3, 4, because it's got 4 valence electrons, right? So when you look at carbon, carbon has a space to receive an electron here, 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 and here. So this can receive 4 electrons. All right, you with me so far? So what happens is, to kind of divvy everything up, okay, is we have hybridization. What that means is that the s orbital and the p orbital combine. Right? They combine. So what happens is this becomes this. And then the electrons are distributed as such. This new orbital is called an sp orbital. Okay. This is now what we call a hybrid. Oh man, why did it do that? This is now called a hybrid. Okay. So when you have the hybrid orbital, okay, now carbon has the space necessary to receive those 4 bonds, or those 4 electrons. Gonna take a screenshot here for you guys. Just give me a second. Okay, hang on, there we go. Okay. Let me hide this real quick. I'm gonna zoom out for a second. Oh, wrong way. All right. So we call this type of hybridization sp2 hybridization. Now there's three types of hybridizations. Okay. There's sp1 hybridization, there's sp2 hybridization, and there's sp3 hybridization. Okay. So all these types of hybridizations exist. Now you got to be able to tell the difference between the three so you know exactly what this is asking for. But because in this question, you need to identify what type of hybridization is existing on this atom right here. Okay, so that's why I needed to get the screenshot for you guys. All right. Here's carbon that as we know it. And this is also in your notebook, by the way. Oh my God, this computer is so slow. I'm sorry, guys. There it goes. Okay. So this is an image of carbon. Right? And this is pretty much explaining everything that I just kind of went over here just a few minutes ago. Okay. So as you can see, carbon has room for four bonds, right? And it achieves that by doing this hybridization. All right. Now, how do you determine whether it's sp1, sp2, or sp3? Okay. If it's sp3, it's going to have four domains, right? So it can exist as four single bonds, okay? Three single bonds and a lone pair of electrons, two single bonds and two lone pairs of electrons. But basically, it's going to have four domains in which to bond, right? sp2 is going to be, you guessed it, two single bonds and one double bond. One double bond and 2 lone pairs. Or 1 double bond, 1 single bond, and 1 lone pair. So 1 double bond, 1 single bond, and 1 lone pair. Now, I want you guys to kind of pay attention to the pattern here, lone pair, okay? All these guys are adding up to 4 domains. It's just the way that they're being distributed, right? That's what you got to pay attention to when trying to determine if you guys are, if you're going to be doing SP hybridization, okay? But it has to add up to 4 bonds. So for example, if I'm looking at SP1 hybridization, right, it would be something like 1 triple bond, okay, and a single bond, or 2 double bonds. Okay, because it's only going to have 2 domains with which to bond. All right, so looking at the different types of hybridization, let's take a look at our molecule and let's figure out what we have. Here's carbon, right? Here's carbon. What do we see on carbon?
2 single and 1 double.
2 single and 1 double. 2 single and 1 double. So let's take a look here. Okay, so what I'm seeing here is sp2 hybridization, right? sp2 hybridization, because what we have is we have 3 bonding domains, right? And those bonding domains exist as 2 single bonds and 1 double bond, right? sp3 would be 3 domains, 4, right? 1s and 3p, right? So this is 4 domains. This is 3 domains. And this is 2 domains. Right? Remember, a domain is an area of bonding, right? Or electron density, right? Remember that lone pairs also contribute to a domain. Remember when we talked about this, when we did Lewis structures, right? That's all this means. So depending on how your bonds and how your lone pairs are set up is going to determine how many domains you have on carbon. Now, right here, we can clearly see that carbon is exhibiting 3 areas of electron density. 1, 2, 3. Right? That's kind of like the shortcut. If it would have been carbon like this, right, with 4 domains, then it would have been sp3 hybridization. If carbon had been shown like this, well, bonded to whatever, where you only have 2 domains, this is sp1, right? So remember that S is 1 domain, P is 1 domain, so 1 plus 1 equals 2 domains. sp2 is S plus 2 p orbitals, that gives you 3 domains, and sp3 is 1 plus 3, that gives you 4 domains, right? That's how you understand hybridization, all right? So if it's asking you for the hybridization of a particular atom, you just got to look at the bonding domains. Now, there's other hybridizations, but in AP chemistry, sp3 is as high as we're going to go. Okay, but that's all it is. It's just a coming together of the s orbital and the p orbital to give you a certain number of domains around the central atom. Okay, that one took a little bit longer because I needed to kind of explain hybridization a little bit. Okay, so that's question number 1, right? Once you understand hybridization and domains, that should be a quick question to answer. Urea has a high solubility in water due in part to its ability to form hydrogen bonds. A urea molecule and 4 water molecules are represented in the box below. Draw 1 dashed line to indicate a possible location of a hydrogen bond between a water molecule and a urea molecule. Okay. So a hydrogen bond is an intermolecular force that forms between positively and negatively charged molecules. Okay. So if we were to take a look at H2O, H2O looks like this, right? When you're taking a look at the atom, the oxygen is the big one that carries with it a slightly negative charge. And the hydrogens carry with it a slightly positive charge. So these guys are slightly positive. All right. So water forms what we call a dipole. Okay. So a dipole is where a molecule has one side that is distinctly negative and it has one side that is distinctly positive. Okay. Because this molecule forms that dipole moment, what happens is when you're taking a look at water molecules, right, and there are in interactions with other molecules, what happens is you form something of a weak attraction, right, called a hydrogen bond. And what happens is the positive side of the water molecule becomes attracted to the negative side of the other water molecule. And that's what keeps water in liquid form, right? So this attraction between positive and negative, right, is what is called a hydrogen bond. This weak attraction, this is what we call a hydrogen bond. There's other intermolecular forces that we're going to go over, but right now we're just going to go over this one to answer this question. So this is an example of what a hydrogen bond is, right? It's not a real bond. It's just an attractive force between molecules that exist between positive and negative charges or sides of a molecule. So here we have water, right? And it is surrounding the urea molecule. Now, it tells you right here that this guy with the lines are nitrogen, and these guys here, these are your hydrogens, right? So how can I draw just a single line to show that there is an attraction? Ooh, it's hard to see the blue one, huh? Between positive and negative, right? That dipole again. Well, you can't do it here, right? Like for this one to this one, because these are both negatively charged, right? You can, however, draw it either here, right? That's an example of a hydrogen bond, right? Where you have an attraction between positive and negative. Let me go ahead and erase it real quick. You can draw one here. You can draw one here, right? These two wouldn't attract, right? Here and here, because they have the same charge. So you wouldn't be able to draw a line there, right? What they want to recognize is that you understand that a hydrogen bond exists between those oppositely charged particles. Okay, so you would just have to draw a single line to represent that. Go ahead and erase all this. So you can just do this. And that's it, right? This is just want to show that you understand that there's an attraction here. Now, ladies, please don't be afraid to ask questions. All right, if you don't understand something, like speak up. Okay, if I'm going too fast, if I'm going too slow, let me know. All right. Oh man, what did I do? Okay. The dissolution of urea is represented by the equation above. It's this one here. A student determines that 5.39 grams of urea, molar mass 60.06 grams per mole, can dissolve in water to make 5.00 milliliters of a saturated solution at 20 degrees Celsius. Okay, this is still all question one, by the way. That's why they give you so much time. Calculate the concentration of urea in moles per liter in the saturated solution at 20 degrees Celsius. All right, now, before I solve this one, I want you guys to, because you guys should know how to do this, right? I want you guys to try and figure this one out, okay? And see if you can answer this question. All right. Ask yourself if you see, if you have any red flags of something that you remember. All right, real quick. Can somebody unmute and tell me what formula you're using to solve this question? No? Nobody saw that this is a molarity question. Okay, so let's take a look at the molar mass, right? So as the student determines that 5.39 grams of urea can dissolve in water to make a 5.00 milliliter solution. So already, if I have moles and volume, I got to recognize that this is going to be a molarity question, right? So let's take a look. If I have 5.39 grams, I know that with my molar mass, right, I can convert that to moles. I have no idea why my computer just did that. Right? Calculator here. Okay, so this is where we're at. So now we got our moles, right? Okay. The formula states that molarity, or the concentration, is equal to the number of moles divided by the volume. So if I have my moles, I'm gonna see, it should be 3 significant figures. So I'm gonna round up to, let's see, 1, 2, 3. So that's gonna round up to 90.090. All right. Now, remember, right? Don't get caught up in this trap, because this 0 right here is just a placeholder. So technically, it's not significant. Okay. So we have to round to this number here, which is the 7.0897, using this number here, which is below 5. So the number stays exactly the way it is, like this. Okay. Remember, the zeros at the front are just placeholders. They're not significant. So we have 3 significant figures. These numbers here are significant. Okay. Okay. So 0.0897 divided by, I got to transfer this to liters. So 1, 2, 3.00500. Okay, these are your significant figures here. 5.00500. 17.94887. Okay, this number here takes this one below 5. Therefore, it is 17.9 molar concentration. You get awarded 1 point for that calculation. Okay. In the last way, I would be, yeah, basically 1 point for each calculation. 1 point for the calculating the correct number of moles, and then 1 point for the concentration. Question so far? Give you guys a second to catch up. I'm going to scroll this up a little bit though. I'm going to type this in actually. Ooh, it's big. My goodness. Okay. Are we good? The student also determines, oh, this question D also determines that the concentration of urea is saturated in a saturated solution at 25 degrees is 19.8 molar. based on the information. Is the distillation of urea endothermic or exothermic? Justify your answer in terms of Le Chatelier's principle. Okay, so Le Chatelier. We went over Le Chatelier's principle briefly in first year chemistry, but we didn't get a chance to cover it because we didn't go back to school. So I'm telling you guys, it's been a rough year. Andrea, I think you remember, I think you saw this in your class because I think we covered it in your class. But either way, what is Le Chatelier's principle? Le Chatelier's principle, and this is going to be exactly the text that's in the definition, right? This is also known as the equilibrium law. Okay, and wow, equilibrium law states that when a system experiences a disturbance is something known as a change in concentration, temp, or pressure change. That's what it means by disturbance. It will respond to restore equilibrium, a new equilibrium. Okay, make this a little bit smaller. Okay. This is so aggravating. Okay, there we go. And now we just learned that I'm a terrible typist. Okay, so when a system experiences a change, right, whether you're changing the pressure, you're changing the temperature, you're changing the concentration, the system itself will fight to restore a new state of equilibrium. It's going to balance itself out again, right? Now, there's a few ways to determine whether something is going to be in terms of energy and temperature, pressure, whatever. Okay, so here's a couple of hints. All right, I think I need a new computer, guys. All right. Okay, so when the system tries to go back into equilibrium, right, it kind of does the opposite of what's happened to it to bring it back into balance. So when we think of a endothermic reaction, okay, an endothermic reaction absorbs energy, which means the temperature drops. An exothermic reaction releases energy, right, which means temperature rises. So in this question, right, what do we see has happened to the temperature? The temperature has gone from 20 degrees to 25 degrees, okay? So in order to bring itself back into balance, right, it's going to absorb energy. It's going to become an endothermic reaction to counteract what we've done to disturb the system. So it says here, based on this information, is the dissolution of urea exothermic or endothermic? Justify your answer in terms of Chatelier's principle. So the justification here would be that an increase in temperature, in order to bring itself back into a balance or a state of equilibrium, according to Le Chatelier's principle, we would see that would favor an endothermic reaction in the system, right? To bring it back into balance. Does that kind of make sense? It's kind of like the opposite, right? I know, guys, it's kind of brutal. I know, I get it. Okay, if there's no questions, we're going to move on to the next one. The equipment shown above is provided so that the student can determine the value of the molar heat of solution for urea. Knowing that the specific heat of the solution is 4.18 joules per grams degrees Celsius, list the specific measurements that are required to be made during this experiment. Okay. Oh, I'm sorry. It says E. I read it as C. Knowing that the specific heat of the solution is, list the specific measurements that are required to make during the experiment. And here it gives you the heat of formation is, where the hell's my, 104.6, right? So this is the heat of formation. All right, for urea. All right. Now, this goes back to when we were doing energy. Do you remember this unit when we were doing energy? Okay. Does any of this equipment ring a bell? This has to do with calorimetry. Remember the calorimeter? You get the cup, fill it up with like water, you drop something in there, and then you calculate, or you find how much energy is absorbed by the water. Okay. So for this experiment, right, what are we going to use? We're going to use a polystyrene cup. We're going to use a thermometer, right? Bottle of urea, obviously, and the balance, right? So obviously we're going to need the mass of the urea. Mass of the water, because we're going to do the calorimetry. Okay. The initial temp of the water and the final temp of the water. See how much energy the water is absorbed. See, it's not asking you to do any calculations here. It's just asking you to kind of like set up the experiment. And let the screen catch up for a second. All right. So if you understand the calorimetry, right, all it's asking you to do is say, hey, what measurements am I going to need? Okay, so we know all the equipment that we need, but the measurements would be the initial temperature, the mass of the water, and the mass of the urea. That's it. That's all it's asking you to do in this question, right? Scroll this up. The entropy change for the dissolution of urea, delta S the enthalpy change of the solution is 70.1 joules per mole Kelvin at 25 degrees. Using the information in the table above, calculate the absolute molar entropy of the aqueous urea. We touched on entropy, but we didn't get that much into it. So this one, I'm going to just kind of give you like a crash course reminder of how to set it up, okay, and then solve it. It's actually a pretty simple formula. It's funny, these guys use delta S, but when we did it in class, we used delta H, remember? But it's the same thing. I just want to point that out. Is equal to the products minus the reactants. You guys remember this formula? Should be in your notes. All right. Okay, so let's take a look at let's scroll up a little bit. Oh my God. And see if we can take a look at the original equation. Oh, it's right here. Okay, so here's your equation, right? Your equation is the dissolution of urea. So basically it goes back and forth in equilibrium. Okay, it's pretty much essentially the same thing. It's just moving back and forth and it's changing from a solid to aqueous solution, right? Then it goes forward, it goes backwards. So your products and your reactants are going to look pretty similar. Okay. You have this value here and it's looking for this value here. Okay. Now, this is the formula that you're going to use. Okay. So all we're going to do now is plug everything in. Plug everything in that I want you to solve. So it's going to be 70.1 joules per mole K is equal to the products. In this case, the product is the unknown, right? So we're going to leave this as the products minus the reactants. And this one, we have it. It's 104.6. And this is in joules per mole Kelvin. Now, this you should be able to solve. So I'm going to give you guys the opportunity to go ahead and make this calculation. Solve for this guy. When you have an answer, let me know. Ah, yes, correct. So in order to solve for this, what I'm going to do is I'm going to add 104.6 joules per moles degrees Kelvin to both sides. Because the units are the same, of course, you can combine them or you can add them. And if you add those numbers together, these cancel here. So 174 point, what'd you get? Oh, I have it here, 0.7. Questions? Okay. Delta S represents the entropy of a solution. Entropy is the level of chaos or disorder. Okay. When you think of entropy, think of something like something organized going into disarray, right? So if you have like a block of ice, right? We'll call it ice. And that block of ice is beginning to melt. Right? Melting. Then what's happening here is the order is moving toward disorder. Right? Because what's happening is in a solid structure, your compounds are very packed together, right? They're in a rigid frame. They don't have much movement, right? And they're solid, right? When that begins to change from a solid to a liquid, from a liquid to a gas, then what you're doing is you're taking that ordered, organized shape and you're introducing disorder, okay? So as you're introducing disorder, what's happening is the level of chaos or the level of entropy is going up. So melting, for example, of ice equals a higher entropy. Or delta S, right? So as you increase the entropy, you're increasing the amount of disorder in a system. Now, if you're going the other way, if you're freezing, for example, or condensing from a gas, right, then you're increasing or decreasing disorder. And what that means is that entropy is going down. Entropy is decreasing. All right. Now, in our formula, I want you guys to pay attention to the reaction, right? Because the reaction says that we're taking urea, if I can find the formula real quick. Urea solid and it's going to urea aqueous. Right? So in terms of entropy, are we seeing an increase or a decrease in the amount of entropy in the system? You can chat if you don't want to unmute. It's easier to unmute. Yeah. Say it again.
Increase.
Yes, we're increasing the amount of entropy, right? So when you're going from a solid urea to an aqueous solution where you're increasing the amount of disorder, then what we're doing is we're increasing the amount of entropy. So here we have an increase in entropy of the solution. And what that does is if you correspond here, we can see that entropy is positive. If entropy is positive, that means that we have an increase in entropy, right? We have an increase in disorder. And what we're seeing here is because the entropy is in fact positive, because that's what we calculated, we can verify or we can confirm that the increase in entropy for this reaction is an accurate assessment of what's going on. So with that newfound knowledge of entropy, let's take a look at what question G is asking. It says, using the particle level reasoning, explain why delta S, or the entropy of the solution, is positive for the dissolution of urea in water. And that's exactly what we did. That's exactly what we just explained. Because you're going from a solid to a liquid, what you're doing is you're increasing the amount of disorder in a system, okay? And because now you have a greater number of possible arrangements of these different molecules, right? Because they're not in a fixed position, then we can confirm going from a solid to a solution would give us a positive value for entropy, right? So without even knowing it, we answered this question here, okay? But now you understand what entropy is, at least I hope you do, right? If I have, oh, here we go. Let's do some ice water, right? And on the exterior of the ice water, I begin to form condensation, right? Condensation from the air. Would this have a positive entropy or a negative entropy?
Negative.
It would be a negative. Exactly. Exactly. That would be a negative entropy. Okay. This is the last formula here that you're going to see in the AP level chemistry that has to do with energy. This should round us up. Okay. Take a minute, write that down.
Mr. Villanueva,
Yes,
I have to go, but I had a question for the test tomorrow.
yes,
Do we have to take our own calculator?
take one. Take your own calculator, just in case, if they provide you with one, then don't worry about it. You just keep it in your bag. But you don't want to be in a situation where you need one and don't have it. And then, it's better to have it and not need it.
Okay, well, do you know, because I have this one, but it's my calculus one. So I don't, it's a graphing calculator, but I also have the TI-84.
Take both. For the last couple of tests that we've been doing, they've been using those or inspires or something like that, right?
Yeah, it's an Inspire.
Yeah, they haven't had an issue with them. You're gonna get a formula sheet with your test and everything. Take both, and if they provide you with one, awesome. And if they don't, then you'll have, just ask them, hey, which one can I use? They'll probably not let you use the Inspire. They'll just have you reset it.
Okay.
Right. So if you have a bunch of stuff in there you don't want to lose, don't take the Inspire because they're gonna make you clear out everything before you use it.
Okay.
All right. I'll upload this a little bit later once I'm done, right? When everybody, then I'll upload it. Okay. Keep practicing. I'm sorry. I want to apologize to you in advance. We should have done a better job this year, but it's been really rough. So just good luck tomorrow. All right.
Thank
All
you.
right. How are we doing, ladies? Are we good?
Yeah.
Okay. All right. So equilibrium. All right. Equilibrium means that an equation goes in both directions. Okay. It means it can either go to the right or it can go to the left. This equation helps you determine which direction it's going to go, right? If you have a positive value or a smaller value for delta G, right? If delta G is small, then the equation moves to the right. If delta G is big, then the equation moves to the left. You don't have to do a calculation. So let's take a look at this one. It says the student claims that the entropy for the process contributes to the thermodynamic favorability of the dissolution of urea at 25 degrees. Use the thermodynamic information above to support the student's claim. What the hell does that mean? It's fancy talk for saying, hey, is the equation going to move to the right or is the equation going to move to the left, right? Okay, you with me so far? Okay. Thermodynamic favorability of the dissolution. So remember the equation, it goes from solid urea to aqueous urea. So this represents dissolution, right? It's dissolving. So it's asking you, is it going to be thermodynamically favorable to move to the right, or is it going to stay, or is it going to want to move to the left? How do you figure that out? You don't have to do a calculation. You just have to understand what all this stuff means. Okay. This represents Gibbs free energy. And it's kind of complicated, but all in all, this is the way to think about it. Okay. A big delta G means it's going to the right, to the product side. A small delta G means it's going to the left. So in this case, right, in this case, we know that delta S is positive, right? We calculated it. Look, it's right here. Delta S is positive. So because your entropy is positive, and this is your formula, right? This positive number is going to make this guy smaller, right? Because this is going to make this guy bigger. Then it's going to pull, because of this minus sign, make delta G smaller. So because it's making delta G smaller, then this equation is in fact going to move to the right. So to answer this question is, because we have a positive entropy, right? A positive change in entropy, it's going to make delta G or Gibbs free energy a smaller value, right? And because delta G is smaller, it's going to favor moving toward the dissolution of urea, right? So it's going to push the reaction to the right, right? So if you want to get fancy with it, you can say that the positive level of entropy in the system will favor a smaller change in delta G and making dissolution of urea thermodynamically favorable or something like that, right? But that's all it is, guys. I mean, like I said, you don't have to do any calculation. It's just understanding how the system works. Okay. Now, if you come across a problem that is talking about enthalpy, that's talking about Gibbs or entropy, look to this formula, because if it has to do a plug and chug, now you know what the formula is. Okay, and you're gonna have a solution sheet, like a formula sheet with all of this stuff. All right. So look, in this one problem, we've covered like 5 units. You see what I'm saying? All right. Now, I want to make sure that I'm not going too fast for you guys. We're going to go on to question number 2. Do you guys need a couple of minutes to take a breather? Are you good? Do you want to keep going? Do you want to get something to snack on? Talk to me.
Yes, can I go get some dinner?
Yeah, I'll pause the video. What do you think about 10 minutes? 15? You
Yeah,
tell
I'm
me.
just gonna go get it and then I'll be back up here and I'll eat it while I listen.
While you listen? Okay. So I'm going to go ahead and pause the video then. We'll say about 10 minutes.
Yeah.
Perfect. Okay. So we have the reactions, right? We flipped this one because we needed Br2 as a product. So now we've rewritten it. We canceled our electrons. Okay. And then we're going to combine so think of it like a math problem. We're going to combine the reactions. Everything on the product on the reactant side. So it's going to be 2 moles of Br minus, okay, plus Cl2 or chlorine yields to produce diatomic bromine plus 2 moles of chlorine minus 1 ions. Okay. Now, is this equation balanced? Sure. Yeah, it is, right? So yeah, this equation is balanced. So this is the balanced equation that they were asking for right here. Write the balanced equation for the thermodynamically favorable reaction. Okay, so we got that, right? You could have done this with iodine. It wouldn't have made a difference. You could have done it with iodine. The only thing that's going to change is this value, but it's not like you have to have, it's only not one answer. It's the concept. So whether you get this value or the other one, it doesn't matter as long as you do it correctly. Okay. All right. So we have our balanced chemical equation. So now we can do our formula, right? Which one is being reduced and which one is being oxidized? Look at it from here. You gotta look at the species, right? From here to here. And from here to here.
Bromine is reducing and then chlorine is oxidizing.
Okay, so how did you come up with that conclusion?
Because from Br from the reactants, it now is like positive, it doesn't have the negative. So that means
That means
it's gaining that 1 electron.
electrons are negative, remember? So if you're gaining electrons, you would become more negative. Does that make sense? Right? So if I'm going from a negative to a positive, right? I'm actually losing electrons because I'm becoming more positive. So these guys are actually oxidizing. If I'm going from, so this is going from a negative to a positive. If I'm going from a positive to a negative, because what I'm doing here is going from chlorine to chlorine 1 minus, right? I'm picking up electrons. So this guy is picking up electrons. If I'm picking up electrons, I'm increasing my negativity because electrons carry a negative charge. So that means that this guy is being reduced. Yeah. So if I'm going to write the formula for the cell potential, right? Cell potential is equal to the reducing species, which in this case we figured out was chlorine, right? It would be this value here, would be 136 volts, 1.36 volts, right? Minus the oxidizing species is 1.07, right? And if you subtract those, we should end up with positive 0.29 volts. All right. Now, the red flag for the formula, because like I said, you're going to have a formula sheet, right? The red flag for this is going to be if you see this symbol. That's your red flag. If you see that symbol, find the formula in your formula sheet that has this formula. Okay. So plus 0.029, because since the potential for E is positive, right? Then the reaction is favorable. Thermodynamically favorable. If it was negative, it would be unfavorable. I'm not going to write that huge word again. Does that make sense? Kind of. Okay. All right. So let's go ahead and take a look at our notebook, because for the next question, we're going to need the notebook. All right. It says Br, bromine and chlorine can react to form the compound BrCl. The boiling point of bromine is 332 Kelvin, whereas the boiling point of bromine chloride is 278 Kelvin. Explain the difference in the boiling point in terms of all intermolecular forces between the molecules of each substance. Okay. So I'm going to go ahead and let me see if I can share the other screen here. Where the hell's my Zoom? There we go. I need to open up my notebook. No. There it is. There we go. Okay, we're gonna do a quick crash course in intermolecular forces, right? A lot of the questions, even the multiple choice questions, are gonna talk about these, so I wanna make sure we go over these. Okay, so we talked earlier about hydrogen bonds, right? Hydrogen bonds are those bonds that form between the positive and the negative charge of molecules that are called dipole, right? That's an example of what we have here. Those hydrogen bonds are what holds water as a liquid. As you boil water and they begin to vibrate, then those hydrogen bonds break, right? And then water molecules become little individual gas molecules, right? So when you boil water and you see those bubbles forming at the bottom, that's exactly what's happening, right? Liquid water is held together in those hydrogen bonds, the positive hydrogens to the negative oxygen. And I don't know if you can see me or not, but as they begin to vibrate, as you add more kinetic energy, they begin to vibrate, and those intermolecular forces break, and then they become a gas, and that's why you see bubbles. Okay, so that's what we talked about earlier, right? So intramolecular force is an interaction within a molecule, right? So intramolecular, it has to do with like bonding, right? That's something that's happening within a molecule. When you have a force between two separate molecules, right, that happen kind of like on the outside, that's what we call intermolecular, right, between separate molecules. A hydrogen force, a hydrogen bond, for example, would be an example of an intermolecular attraction, okay? This is exactly what we just talked about, and this is the hydrogen bond. We answered that in question number 1, and that's what's exactly what's happening. A water molecule is very polar. It has a distinct positive side and a distinct negative side. And those oppositely charged forces or charges attract one another weakly, but they do attract one another, and we call that an example of a hydrogen bond, right? Okay, so dipole-dipole interactions. This happens when you have two polar molecules. Right? Polar means that you have one distinct positive and one distinct negative. Is this thing moving? Are you seeing the page scroll up, or is it stuck on the water molecules?
No, it's on the water molecules.
Okay, let me see what's going on here. All right. So dipole-dipole interactions happen between polar molecules, right? So a hydrogen bond would be an example of a dipole-dipole. They could be either attractive forces or they can push each other away. But either way, it's still an example of a dipole-dipole interaction between a positively charged pole and a negatively charged pole. All right. Now, when you have a polar molecule or a polar compound come in contact with something that is non-polar, meaning it does not have a distinctly positive or distinctly negative side, then we get an interaction called a dipole-induced dipole interaction. Mister, what does that mean? What that means is when you have a polar molecule, right, that polar molecule has a distinctive negative side and a distinctive positive side. And what that does is because charges work on the basic premise of opposites attract, it can push or attract the electrons within those compounds, right, to one particular side. And when that happens, you form a weak interaction, right? So let me see, there's an example here. Right here. What happens is in a dipole-induced dipole interaction is the electrons, right, because of the positive charge that they see on the outside, it can either be pushed away or gathered to one side. And what that does is it takes a non-polar molecule and for like a split second makes it polar by pushing the electrons either away because it's a negative part, or it brings them towards because it's positively charged, right? And what that does is for a split second creates a slight polarity in that non-polar molecule, and then you get that interaction that happens, right? So when that happens, we call that a dipole-induced dipole. Okay. Dipole. Oh, when one polar, and this happens when you have one polar molecule and one non-polar molecule. We call that a dipole-induced dipole moment. Can two non-polar molecules interact? Okay. So again, non-polar means that you have no distinct positive, no distinct negative, right? Can they still attract one another? And the answer is yes, right? With the same mechanism that we see with a dipole-induced you know what? I got a call. Can you give me a second? I'm gonna pause this for just a quick sec. All right, where were we? What is this going on here? Okay, so we left off with, can nonpolar molecules interact, right? And the answer to that question is yes, right? And it's basically with the same thing that happens with a polar and nonpolar, is that these electrons are kind of moving around, and every so often the electrons are kind of shift to one side or another. And when that happens, you create that attraction, right? So in this example here, all the electrons are gathered here negative, right? The electrons over here have been shifted to the left, and you have a slightly more positive side. So when that happens is you get that weak interaction. This weak interaction between two nonpolar molecules are called London dispersion forces, okay? So even though bromine is nonpolar, right, electrons still kind of move around, and when they get in that same position, in a weird random position where they're either to one side or another, you do create those interactions. London dispersion forces happen between nonpolar molecules, okay? All molecules exhibit LDF, right? That's short for London dispersion molecules. But when you're talking about interactions between like polar molecules, then the London dispersion forces are going to be a little bit weaker because you're going to have a stronger dipole-dipole interaction, right? This is really reserved. This type of interaction is really reserved for nonpolar molecules. And the strength of the LDF, this is important, okay? Is dependent directly on the size of the electron cloud. So in the first part of question number 2, we talked about how iodine had that bigger electron cloud because it has all those energy levels. The bigger the electron cloud, the more likely you're going to have London dispersion forces, and those London dispersion forces are going to be a lot stronger in a much bigger cloud, okay? As the molecules become larger and larger, these London dispersion forces can be pretty strong, okay? So that's why we see things like, and this is exactly the question that it asked, why iodine, for example, is going to have a much stronger boiling point, because those London dispersion forces are going to be much stronger because they have a much larger electron cloud, right? So you have more electrons that are able to interact with one another, and you create a much stronger interaction, okay? Okay, that was it. That's all I wanted to discuss with you on that. So let me go ahead and stop sharing my screen. Okay, we'll go back to our whiteboard here. I'm just waiting for it to load up. I'm sorry. Here it comes. Okay, so the boiling point of Br2 is 332 degrees Kelvin, whereas the boiling point of BrCl, which is bromine monochloride, is 278 Kelvin. Explain the difference in the boiling point in terms of all the intramolecular forces present between molecules of each substance. Okay, I want you to take a few minutes and I want you to see if you can give me a good explanation as to why this is true. Think about all the forces that we just discussed. All right, and see if you can figure out why this is true. When you're ready, just unmute or chat me or something. You don't start it? Oh, okay. So we're both guilty. So yeah, what? Oh, that's fine. And you'll get it? Okay. Okay, that's fine. Sesame, I guess. Yeah, they have sauce. Alright. Yep. Any ideas? No, nothing?
Not really, no.
Okay. So I have my pen. What happened to my pen, Miss Griswack? Oh my God. Oh, it's right here. Okay. So do you know, okay, polarity? Let me scroll this down a little bit. Polarity equals difference in electronegativity. Do you remember what this is? I'm sure I misspelled it. Do you remember what electronegativity is?
Yeah, it's like the attraction to like gain electrons or yeah.
Ah, perfect. Yes, that's exactly what it is, right? So polarity means that the difference in the values of your electronegativity. Now we know that electronegativity going across the periodic table. So like, let's pretend this is the periodic table, right? Goes up here and then we go to the end, this and this, whatever. So this is our periodic table. Electronegativity increases as you move to the right and you move up the periodic table, right? So electronegativity increases in these directions, correct? So when you have elements, for example, that are on this side, bonded to a metal on this side, you have a huge difference in electronegativity. If you have a huge difference in electronegativity, then you have a very polar molecule, right? That's what happens because like oxygen, for example, is here and hydrogen is up here, right? This is hydrogen, this is oxygen. So when you have those two things bonded together, you have a huge difference in electronegativities, right? Big difference in electronegativity. So water is very polar. And because water is polar, we see a lot of dipole-dipole interactions. I'm throwing a lot at you, huh? Okay, so that's how you figure out if something is polar or not. Now, when we're talking about elements, for example, bromine bonded to bromine, right? Are they going to have different values of electronegativity? No, right? Because they're the same element. So because they're the same element, their electronegativity is going to be the same. So like if let's say the electronegativity of bromine is 3 and this bromine is 3, then the difference is 0. So because there's no difference in electronegativity, we get non-polar. Right? Now, if something is non-polar, what's the main intermolecular force that we're going to experience here? What's the intermolecular force between non-polar molecules? Starts with an L. It's a city in England.
The London.
Ah, there you go. Right? Yeah, we're gonna see we're gonna see primarily London dispersion forces, right? Okay. So because we're gonna see London dispersion forces, right? They're gonna be pretty strong because bromine's a pretty big molecule, right? So Br2 is gonna have a pretty strong LDF. Simply because it's a big molecule. Big, non-polar, right? Non-polar. Okay. Now, when you're talking about BRCL, all right, it's going to have two types of forces. Okay. BRCL is still pretty non-polar, but it's not completely non-polar because chlorine has a slightly stronger electronegativity because chlorine is here and bromine is here, right? So because electronegativity increases as you move up the table, right? Then the elements in the same group are going to be slightly more electronegativity as you move up the periodic table. So BRCL or bromine monochloride is going to have LDF because it's primarily not, it's not a polar molecule, but it does have slight polarity. And it's going to have dipole-dipole because it's slightly polar. Because it's slightly polar. Okay. So that slight polarity is very, very minuscule. So the main attractive force is going to be LDF. Now, which one do you think has a bigger electron cloud? Bromine to chlorine or bromine to bromine?
Bromine to chlorine.
Is going to have the bigger cloud?
I think so.
Well, remember, when you're looking at the periodic table, right, you have fluorine. Oh my God. I don't know why I did that. It's catching up. Okay, I'll do it again. You have fluorine, chlorine, bromine, right? So when you're looking at bromine, you're going to have a big cloud to a big cloud. When you have bromine to chlorine, you're going to have a big cloud with a slightly smaller cloud because chlorine's a slightly smaller molecule, right? So looking at it in terms like this, which one's going to have the overall bigger cloud?
Bromine to bromine.
Ah, yes. So this has a bigger electron cloud equals bigger LDF, right? And the bigger LDF equals higher boiling point. Because it's a stronger interaction. Right? The stronger the interaction is, the stronger the bond, the more energy it takes to break those intramolecular forces. Does that make sense? Okay, so I'll let you stew on that for a little bit. Okay. D, so it says here, a 0.1 mole sample of pure bromine monochloride is placed in a previously evacuated rigid 2.0 liter container at 298 degrees Kelvin. Eventually, the system reaches equilibrium according to the equation above. Here. Calculate the pressure in the container before equilibrium is established. Okay, now we started talking about this and you guys did an ed puzzle on this the other day, right? So this has to do with gas pressures. Okay, so the formula I want you to take to memory, okay, and this is going to be on your formula sheet also, is the ideal gas law, which says that PV equals nRT. PV equals nRT. Okay, this is your ideal gas law. P represents pressure. V represents volume. N represents moles of gas. R equals the gas constant. Okay, and T is temperature. Okay, okay. Now it says calculate the pressure in the container before equilibrium is established. Okay, so I can already see here that we have a temperature. We have a volume. Let's see, we have moles. And R is a constant, which is given. Okay, there's two constants that go with the ideal gas law. Okay, and the constants are going to depend on what units you have. Okay, so in this case, the unit that we have for, let's see, we have temperature Kelvin. That's going to be the one that really determines. Okay, so in Kelvin, R is equal to, let's see, I have it written down right here, 0.0206 or 8206 liters at per degrees per moles Kelvin. This is the unit, moles Kelvin. Okay, let's go ahead and write that down. Okay, these are the two gas constants that you're going to see. One of them is for pressure, and one of them is for energy. Okay, since we're looking for pressure, this one here is in joules. The joules is the giveaway. I said temperature earlier, but it's actually joules. So if you see joules, that's got to be the red flag to say that's energy. If you see ATM, that's the one that tells you it's pressure. Okay. So of the two constants, which one do you think we're going to use for this particular equation?
The pressure.
Ah, correct. So if we need to solve for pressure, and our formula says that the pressure times the volume is equal to the moles times the gas constant and temperature, how do I solve for pressure? If I divide both sides by the volume, then pressure is equal to the moles of the gas times the gas constant divided by the volume of the container in liters. Okay, so I want you to take a couple of minutes and tell me what you come up with. What do we come up with?
I'm pretty sure I'm wrong because I got a really low number.
How low?
Because like on the R, is it just like, do you just use the 0.08206 or do you have to like put in like the liters and stuff for it?
Well, the units are going to cancel, right? But you should, well, what did you come up with? Let's figure that out first.
Well, I just used the 0.08, so I just like multiplied all that and then divided it by 2. So I just got 1.223.
That's right.
Oh, okay.
Yeah. So when you have, okay, you have the point, what is it, 0.1 moles? All right, 0.1 moles times the gas constant, which is 0.08206 liters, atmospheres over moles Kelvin, right? Then you multiply that by the temperature, which is what was it, 298K? And you divide all that by the volume, which is 2.00 liters. Right? What happens? Come on. Hang on. My computer like went white. See? Here it comes. Okay. When you do all that and you divide by the volume, look what happens to all the units. Right? Okay. I wrote this before, but okay. 2.00 liters. So liters cancels here. Moles cancels here. Kelvin cancels here. And you're left with atmospheres. So your answer should be 1.22 atmospheres. Okay, so yeah, you're correct. All right. Now, there's a couple of laws. Okay. The first one, the one we talked about is PV is equal to nRT. The other one is pressure PV1, P1 V1 equals P2 V2, right? So this is initial and final. So if you have a problem that has like no temperature, no moles, just straight pressure volume, you use this formula. All right, and then the other one is pressure and temperature. Right, this is when you have just pressure and temp. And then the last one, and these will all be on your formula sheet. So you don't have to memorize these, right? But I just want you to know what they're used for. This is called the combined gas law. So if you're working with a scenario where you have pressure, volume, and temperature, but you don't have moles, right? Then you use this one, which is the combined gas law. I don't know why it's not showing up on your screen, but I have it written down already. There it goes. Okay, this is the combined gas law. So this is when moles are constant, right? So moles equals constant. This one is when volume is constant. Meaning volume doesn't change. And this one is when temperature is constant. Meaning temperature doesn't change. Okay. And you'll have that. You'll have questions that will say, if temperature is constant, what would be the final volume if the pressure is increased by like this or something like that? Okay, so you don't have to memorize these, just know when they're going to be used. Okay, that's it. Questions so far? It's a lot, huh? Yeah. Okay, listen, you can wave the white flag whenever you're ready. Okay, all right. Let's move on to, so at least get number 2 done. Okay. Write the we're part D. Write the expression for the equilibrium constant KEQ for the decomposition of BrCl or bromine monochloride. Now, remember that we already have the equation. So when they say the decomposition of bromine monochloride, that's just them trying to be fancy. And they're just talking about this reaction right here. See, this is the decomposition of bromine monochloride right here. That's all it is. Okay. Now, the equilibrium constant has to do with the concentration of the compounds. Okay. So I'm going to scooch this over I should probably label these, huh? All these solutions. So for E says write the equilibrium constant. Okay. So there's a very simple formula for this. Okay. The equilibrium constant is equal to the concentration of the products divided by the concentration of the reactants. Right? And then the moles or the coefficients are exponents. Man, this delay is ridiculous. There it is. Wow, that took almost 20 seconds. Okay, so by following this very simple formula, you can write the concentration constant, right? The equilibrium constant. All right, so let's take a look at our reaction. Here is our reaction, okay? It is 2 moles of bromine monochloride. This is in gas form, okay? Is in equilibrium at, to produce bromine, right, which is a gas, plus 1 mole of chlorine 2, which is also a gas. It looks like an AQ, so I'm going to just rewrite that real quick. Okay, so this is our reaction. All right, you with me so far? All right, so we know that these are our reactants, and we know that these are the products, correct? So if I'm going to write this question or this equilibrium constant, all I have to do is put the products over the reactants in this format. So my equilibrium constant is equal to the concentration of my products, which is in this case Br2 times Cl2 all over the concentration of the products, of the reactants, which in this case is BrCl. And because there's a 2 right here, that gets an exponent of 2. That's it. That's all you have to do for that. All right. So this here represents equilibrium constant. Questions? All right. Pretty simple, pretty simple. Okay, F. After the system has reached equilibrium, 42% of the original bromine monochloride sample has decomposed. Determine the value of the equilibrium constant for the decomposition reaction of BrCl or bromine monochloride at 298 degrees Kelvin. Okay. Let me take a look here real quick. There's the pressure. Okay, do you have your calculator with you? Let me see. All right. This was going to take a little bit of algebra to do. All right, I'm going to explain to you a couple of basically, once you calculate your equilibrium constant, then you have to calculate it. What we're going to do now is we're going to figure out this value right here. Okay. All right, I want you to draw this table. And we did this in class, but really early on. Let me scroll this up. Okay, I want you to draw this table.
Bless you.
Okay, yes, thank you. I'll give you a second to draw.
Mister, is this one gonna take a long time? Because I have to leave in like a couple minutes.
If you want, we can set it up and call it a night. Yeah?
Okay, yeah.
Okay. So here is our reaction. Okay. So it is 2 BrCl goes to equilibrium to produce Br2 plus Cl2. Okay. All right. Now, we already calculated that the pressure, right? The pressure of BrCl2 is at 1.22 atmospheres, right? So that's 1.22. That goes there. This is our starting. Now, these two guys are forming, so they're not going to have an initial value of anything, right? This is where they begin. All right. Now, because now the C represents change. So this is your initial, this is your starting point. How is it changing? How is this reaction changing? So for this one is breaking down to form these two compounds, right? So this one is gonna change by a value of 2x, right? Because it's breaking down, it's gonna be a negative. Since these guys are forming and there's only 1 mole of each one, this guy's gonna form by a plus x, and this guy is gonna form by a plus x. Okay. The equilibrium is how it's changed. So we said it decomposed by 42% or 0.42. So 0.42 of 1.22, that gives you 0.51, right? And if you take 1.22 minus 0.51, you end up, so here you get, because it's decomposing, right? .71. All right. Because let's see, what is it? 0.42 2x equals 0.51. Then x must equal 0.26, right? Because if you divide by 2. So each one of these has changed by 0.26 to get to equilibrium. Yeah. All right. And that's it. So to find the value, then we take our equilibrium constant, right? In this case, it's 0.26 because that's the value of each one in the products, divided by 0.71 squared. And if you work that out, you should end up with 0.13 equals KEQ. Okay, that's it. That's it. All right. Don't stress about it. Okay, go in there and do the best that you can. All right, you got a lot today, and we covered the stuff that's going to be half of the test. Okay, go in there, do your best. Don't stress about it. All right, and whatever happens, happens. Either way, though, I'm glad that you took this class. I wish it would have been a different year, but I'm glad I had you another year. All right, tomorrow, take the day off. Don't come to chemistry, to AP chemistry. Just take your test in the morning, and then you don't have to report to class. Okay. All
How
right.
long is the test? Is it like 3 hours or what?
Yeah, it's gonna be like an hour and a half for this portion, and then like about another hour or like 70 minutes for the multiple choice.
Okay.
All right. Get some sleep, eat well. Let me know how it goes tomorrow, okay? All right. Night.